the main subject of this entire video, just to sum it up, is that if you treat current as though it's velocity, as in meters per second, it ends up being the case that the Newtonian physics can perfectly describe direct current, just from Ohm's laws. Now, I have no problems at all with what he's saying. As a matter of fact, I think I probably have more evidence to support that his theory is true. And where my evidence comes from is, well, we kind of have to talk a little bit more about field geometries to really get the idea. So this is a short image that kind of gets, or a short diagram I put together that kind of gets the general idea across. So they have two different types of geometries. You have your radial geometries, where you have these lines that are coming out, and of course the opposite charges repel, so their radial lines tend to pull away from each other. And then they're for dissimilar charges, the radial lines pull towards each other and kind of cancel each other out. And so you end up with this geometry. And then, of course, you also have your concentric geometries, where you have these concentric rings that are around a pole. And then if the currents are going in the same direction, the field lines create closed loops around the wires. And if they're going in opposite directions, you end up with this almost owl's eye-like image. And there's two different ways in which these things can be constructed together to overlap. The first way is you have this repulsion between the similar charges and the currents going in the same direction, which results in this image right here. This image doesn't exist anywhere else on the internet, as far as I know. I'm the first person to put that together. But this right here is an image that has shown up before in a book by Charles Proteus Steinmetz called Electrical Discharges, Impulses, Waves, and Other Transients. And why these field geometries matter is because these things actually physically manifest in the real world. You can do experiments where you can actually see these things, which we can see over here. Here we've got a wire that's coming up out of a board, and there's a current that's passing through this wire. And what happens is you end up having a concentric rings, a magnetic field of concentric rings around the wire. And if we take a loop of wire and we do the same thing, so you have a loop of wire coming out of the board and then going into the board, so the current's going in opposite directions once it gets to the other side. But anyway, you see we have these concentric rings, which correlates to this over here. And if we look at a bar magnet, we see if we take two magnets that are dissimilar and we push them towards each other, we end up with this image right here, which correlates to this. This is the repulsion between similar charges. So you have radial geometries here. And of course, if we look at the dielectric field of a magnet using a CRT screen, so we just hold it up to a CRT TV, lengthwise we'll see that we have the owl's eye images as well. So it's the inverse. Now you're looking at the electric field rather than the magnetic field. In this right here, this image is probably a bit confusing to tell what it is, but what it is you have a ferrocell, which is basically there's a ferrofluid that's trapped between two glass plates, and it's lit up with LEDs or lights or whatever. And then you have a magnet that's underneath it, and results in a refraction of the light where you can see the electric field. And then on top of it, we have some iron filings sprinkled. So what you can see is these iron filings are correlating with this right here, and the electric field is correlating with this right here. And so if you overlap this and this, what you get is this image. But the most peculiar thing about this is that, if we can get back into here for a second, for a single bar magnet, you can see that the geometry looks like this, right? But if you look at a wire, like a loop of wire, it's the exact opposite, the conjugate geometry. Instead of being radial coming from both sides, it's concentric coming from both sides. And so that's the first thing that I noticed when I was doing this, was that the magnetic field of a magnet seems to have the same geometry as the electric field of a wire, and the electric field of a magnet seems to have the exact same geometry as the magnetic field of a wire. They're exact opposites of each other. The second thing I noticed, which is actually on this diagram, is that this image, the Wolf StereoNet image, is actually a stereographic projection of a sphere onto a plane. So if you take a sphere and say like you're on the plane itself right here and you're projecting points out, what you end up seeing is this. So if the best way to try to understand this is be like, if I covered up part of it like that, right? What you're looking at is the top of the sphere. Like if you tilt your head 90 degrees, what you're looking at is the top of the sphere. And if you tilt it the other way, what you're looking at here is the bottom of the sphere. So that's just an easy way of seeing it. So what you're looking at when you look at this whole image, you're basically looking at the inside of a sphere. And this really got me thinking when I first noticed this, because it reminded me of a diagram that I'd seen in the past, which is where you can invert a cylinder over the surface of a sphere, and you get a torus. And of course we know that these geometries are related. But what I find most peculiar here is that say that this blue cylinder here represents a conducting wire, right? And you have an electrical current that's passing through the wire going up in this direction. Equipotential lines of force that are surrounding that wire, basically points that are the same distance, or have the same energies based on the distance, which is like an inverse square from the wires, should be almost producing like this this toroidal shape. And so when I started thinking about like the way that these things are all connected, this idea occurred to me that it could be possible that the magnetic field is actually a store of the charge, of the momentum of the charge. And it makes more sense when you start to consider that that an accelerating charge creates a magnetic field, because if the current is increasing, which means that it's accelerating, the momentum should also be increasing, but otherwise it would be conserved. So it's the same thing. Like if the momentum is decreasing, it has to be losing some energy to a force. And there's just some other interesting things as well. Like if you've ever seen these things, they're called Moir bezels. These are just two radial lines. Like they're the same thing as these right here. So basically if you move one of these past the other, you can see you have these concentric eyes, which is basically that. You're just looking at it sideways. It's 90 degrees. And another thing as well that I had noticed from this is if you've ever seen a diagram of something, it's called a hypersphere or a globe. You're looking at the parallels and meridians of a four-dimensional sphere. So this is really peculiar because one, this right here looks just like the oh hell, what do you want to call it? It looks like a three-dimensional image of what this is. That weird bulbous shape that you're seeing in green here looks almost like a three-dimensional expression of this. And if you're looking at just one of these from top down, like if you're looking at the concentric view, it seems like it would correlate just with like this red image right here, and then this toroidal shape, which is perpendicular to both of these two, looks just like the torus that you would see here. So you can see where all of these different ideas are all tying together, like geometrically speaking. And the main thing that I kind of pulled away from this is that what you're looking at when you're looking at the electromagnetic field around a wire, or a sorry, my brain's blinking out. I think my blood sugar's high or something. But when you're looking at the electromagnetic field around a wire, what you're looking at is you're actually looking at a partial field. What we call a charge is basically a partial field. It's like you've cut off part of what it is. And the best way to see that is like if you're looking at these. Like these are when we think of a charge, we think of these radial lines that are coming out in all directions. But the thing is that these lines of force always exists between two objects. It doesn't exist between one. So this can make sense if you're talking about the energy of the thing, but where the field lines terminate, is where you start getting these geometries from. So when we're talking about charge, what you're actually talking about, you're looking at like a partial field geometry. And so as a particle accelerates, it generates a magnetic field. I mean, charged particle as it accelerates, it generates a magnetic field. And an alternating magnetic field can also create, or a changing magnetic field can also create an acceleration. So just where all of these things tied together, it's like I said before, like my approach from coming to this is that I was looking at the geometries of these different fields and realizing that they have to be spherical in some sense. They have to terminate, and which means that there's no divergence in the force, but there can be a divergence in the energy. But my thoughts on this was that the magnetic field was actually related in some way to the momentum of the electric charge. And that makes a lot of sense in the context of the theory that was done by Jeff Yee, talking about how current is nothing more than the velocity of the electric charge, the average velocity of all of the particles. But anyway, this video is, I guess I could say I could probably cut it off around here. That's most of what I had to say about the subject, and I'm not really in my A game today as far as my mind is concerned. But anyway, that's about all, so thank you for watching.